Today we're going to talk about end-to-end machine learning across multi-cloud. So we actually do the training on-prem, and then we do what we call as transfer learning in AWS Sagemaker. So I have a colleague from AWS here, Rakesh. Why don't you introduce yourself?
Thank you, Mohan. Good morning, folks. My name is Rakesh Ramdas. I'm a solution architect in AWS and happy to present out here with Mohan today. Sahil?
All right.
Hello, everyone. My name is Sahil Thapar. I'm a solutions architect at AWS.
Thank you, Rakesh and Sahil. So let me share my screen and let's get started. So today's topic, as I mentioned earlier, is end-to-end machine learning with training on-premises and inference on AWS. And you see that we're going to use a concept called transfer learning, which we'll describe in detail later. So this is the agenda we have today. I want to just introduce AI/ML important terms and concepts so that people new to this can follow along when we go through the presentation. We look at GPU-based model training. We're going to leverage something called ImageNet that was used for the data set that was using for training. Then transfer learning, Rakesh will go through transfer learning in SageMaker and also leveraging AWS SageMaker endpoints, and then we'll summarize at the end. So as you can follow the industry, there's a massive explosion in the amount of machine learning and AI that's come about in the past few years, primarily due to some of the developments in compute that help AI/ML. And when I did my master's a couple of decades ago, I did AI/ML, and that never took off. But now you see it being used across all these industries, including manufacturing, retail, healthcare, travel, financial services, and energy and utilities. So you see it everywhere. You actually use it when you're using an Amazon Echo or Siri on your iPhone. So all these are forms of AI/ML that are deployed in our day-to-day lives. And so, but in addition to that, all these applications can have a major impact in the enterprise. And so, if enterprises do not adopt AI/ML, they stand to lose. So it's important. It's a competitive aspect that they need to make sure that they're able to leverage AI/ML to learn from learn from the data they have and use it for betterment of whatever they're doing from a business perspective. So now let's look at artificial intelligence, right? What is that? We'll define a few terms here. AI, so any technique that mimics human intelligence is called AI. So it's a big field, and it's been in existence since the 1940s. So that field has been existing. And then we have machine learning, where we actually using mathematical techniques and data to predict more and create models that can mimic human behavior, right? And then last but not the least is deep learning. So in the deep learning, we're actually emulating how the human brain makes decisions. So it leverages something called neural networks, and the neural networks represent the neurons in the human brain. And here we have large sets of data, and then we use that data to predict and create models. And then there are different types of deep learning and machine learning, and we'll go through all these aspects shortly. So the other aspect is dependent on the machine learning and deep learning require a lot of data. And you know that in the past few years, there's been an explosion of data. And so because this data is available, we are able to create better models and use these models in day-to-day applications. So now let's look at how traditionally applications used to process data. There used to be a program, there's a data, and then the application would provide answers based on what is being programmed into it. So usually there are subject matter experts that help create the application, because they tell the program what, based on the data, what the answer should be. So in the case of machine learning, things are a little bit in a different order here. So we have data, and then there are answers that, for example, data already exists, and some subject matter experts label the data. That means they're saying, they give you the answers for what the problem is trying to solve. And then by using the answers, the machine learning is able to create a model on how, and learn from it and say, the next time I see similar data, I know what answer to give. So that's kind of the machine learning model. So we are moving from what used to be traditional application to this new machine learning model. So if you look at the technology landscape, right? So there is machine learning, like we mentioned, and then there are different kinds of machine learning. The first one we look here is what we call unsupervised learning, where there is no subject matter expert labeling the data. That means there's nobody who has given the answers for different problems that can be gotten from the data. So the machine learning algorithms look at the data and look for patterns in the data by themselves, and then they come to conclusions, and then they look at they kind of, based on that, they're able to come to certain decisions based on what they see in that data, and that's what unsupervised learning gives you. Then we have supervised learning. This is more common. This is where for example, let's take radiology as an example, where there are X-ray scans of chest scans of people, and then the radiologist is able to look at the data and say if there is chest infection or not, right? And so so based on a lot of the results, the chest scans they've looked at in the past, they're able to say whether somebody's got pneumonia or not, for example, right? And then that is labeling. That's what we call as labeling. So they take that data, and we can look at that past history and then feed that data with the labels of either the yes or no, for example, for pneumonia, and then pass that on to a machine learning model, and it can learn from that and model from that. So that's kind of what supervised learning gives you. And third area is reinforcement learning. This is what we reward behavior. So what happens is we have the machine do certain tasks, and when it does it in a particular way, we reward the machine, and through that reinforcement, learning happens. So a lot of the things like recently the AI models have been able to beat the champion in the game called Go. That's because of reinforcement learning. So a lot of the skills training, skills acquisition and stuff, other things like robots also, for example, use reinforcement learning. So we reward the robot when it does something right, and punish it when it doesn't. So that through that kind of a behavior, you come to reinforcement learning. So supervised learning, we already mentioned a little bit about it, and so it's based on labeled data sets. So the data set has to be labeled, and here you see an example of supervised learning where you're actually looking at intrusion detection. So from a security standpoint, we see that there are intrusions. This is looking at intrusion data, and we see we take that the first row out there shows that there was an intrusion. So based on the past experience and history, we know that intrusion happened when that event happened. Whereas in the next one, we see that event happened, but there was no intrusion. So we use feed this kind of a data to the AI training algorithms, and then they're able to learn from it, and then become experts at future labeling, or what do you call it, inference. So when you actually take a model and deploy it in production, it's called inference. And so that's kind of what the models are used for. So then the next thing is the most common things you guys are already familiar with probably is like, taking images, and so image recognition. So we feed thousands of images into a system, and then they're labeled either as dog and cat, for example, in this case. And then we have a model, and then the model is then used for inference. And here you can see that in the next slide that the model is able to predict. For example, it takes if you give it a picture that is never seen before, it's able to predict with certain accuracy, a high amount of accuracy depending on the type of model, if it's a dog or a cat. The other type of learning we talked about obviously is unsupervised learning. It infers patterns from the data set. So there is no labeling here. And so what we see here is, think of the left-hand side here. You have an original unclustered data set. Then we use something called a clustering mechanism, where you're able to group things together based on certain characteristics of how they fall from a behavior standpoint. And that's what you see on the right-hand side. So clustering is k-means clustering is a method that's been there for many years now. And so a lot of the other clustering mechanisms also exist. So you're able to infer from the data certain patterns, and that's used for unsupervised learning. Okay, so now let's talk about the process of machine learning, right? The whole aspect relating to machine learning has a lot of steps, right? So you have data. So you have to prepare the data. The data should be in a format where it can be trained on. So if a data is not labeled properly, we need to for example, if you're using it for supervised learning, you want to make sure that the data is labeled and the data set is formatted in the way the programs expect it. So you kind of prepare the training data, and then you have the training data set. Then you take the training data set, and then you use a supervised training in this instance, and then you use neural networks or other aspects that are ideal for that particular model, and you start training it. So you train the model, and then one aspect of data preparation is, let me explain. So when you have, let's say, 100,000 records of data, you want to make sure that you have some records not used in the training, used for validation purposes. So let's say we want to say 20% of the data is going to be used for validation. So we take 80,000 records and use that for the training, and another 20,000 records we separate it out. We never use that in the training, and we use that for validating. So once we train a model, we then pass the validation data through the model, and verify that the model is working, and get it to an accuracy that's acceptable for that particular application. So the accuracy can vary based on the application. So for certain things that's life and death, you need a very, very high accuracy. For other cases, you could live with a smaller accuracy. It depends on the application. So the model can do classification and prediction, right? And then eventually, when you feel that the model is good enough, you deploy it in the form of a user application. And so you deploy it in production, and then the model is doing something what we call as inference. So inference is where the model is actually actively looking at new data that is never seen before, that's coming in from the application, and making decisions based on what it knows. Then let's say the model works for most of the situations, but sometimes there are corner cases where the model does not work. So then what we have to do is we have to take those corner cases where the model actually failed to predict the right outcome, and use it again as part of the training. So it's a loop. So you build a model, you put it in production, and wherever you see failures, you take that data and use to retrain the model and make it better. So that's what you see here in the whole machine learning pipeline. So now let's look at VMware and where we stand from a virtualization standpoint for AI ML. So we actually have a AI-ready enterprise level virtualization platform. And so let's look at all the components here, right? So we actually actively work with NVIDIA. We partner with NVIDIA. NVIDIA is the leader in deep learning, primarily at this stage, because GPUs are an essential component, accelerator that we support in VMware that are needed for deep learning. So you have on the top, you have AI data applications, and then we virtualize the GPU. So you will see an example of it on how we did our training later on. And so the GPU we virtualize, there are multiple ways to virtualize the GPU. That include pass-through, where you're actually passing through a GPU device to the virtual machine. Then we have vGPU, which is a way is an NVIDIA developed solution that lets you share GPUs across multiple virtual machines and be able to also have things like vMotion and other aspects working with it. So, and then we are able to also scale. So to some extent, we support multiple GPUs in a server, or if that's not enough, we can do something called distributed machine learning. And so that's kind of how we scale performance. And what we show you in our proof of concept is actually at the training stage, we use something called Horovod, which does distributed machine learning. So the vSphere platform supports both containers and virtual machines. You can have virtual machines access GPUs, and also containers have access GPUs. But to do containers accessing GPU, you have to jump through a few hoops, because at this point in time, the container doesn't, we cannot really easily map a GPU to a container, whereas we can map a GPU to a virtual machine. But in the near future, we're going to see that the ability to actually map containers to GPUs. So the important thing about the latest version of vSphere 7 is that we support Kubernetes with our Tanzu platform. And Kubernetes is where all our data scientists, developers, and researchers are. They are using these Kubernetes to build their applications. So the fact that we support Kubernetes is a big thing here. And also the fact that we support the technologies necessary for deep learning and machine learning in the form of GPUs and SmartNICs, as you see in the bottom layer. So we already talked about GPUs a little bit. We'll talk about a little bit more on the next slide. But SmartNICs is another thing where you actually have so capability within in the NIC itself, the network interface card, to provide data processing. So those are the upcoming technology that you will see being leveraged for AI ML. And the other aspect is NICs. If you have a high-speed NIC, you can leverage something called RDMA, which we'll also look at a little bit, that provides you accelerated capabilities and less overhead in processing. So now let's look at what we're going to use in our proof of concept, right? So traditionally in ML, you have a data set, you train, and then the data set, the larger the data set, the better the model, right? And then the issue with that is not all data is large. That means, you might have, for example, you might have a lot of images of animals, for example, but you might not have enough images of X-ray scans, for example. And so now there are a lot of aspects of image recognition that are common between recognizing animals and recognizing X-rays. But so there are some things that we can learn from common images that we can build on. And then we take that and then think of it this way, right? You transfer. So you take a large data set, a general data set with a lot of images. You take that and transfer and then build a good model. That model is good from a general sense, right? And then what you do is, once you have that model, you do some more learning on it. You take the model at its final stage, do some processing on the model, remove a few layers in the end, add, and then retrain the model. Retrain the model with specific data for radiology, for example, the X-ray scans. And then you're able to leverage the knowledge from the large generalized model, and then you're able to transfer that knowledge and build on top of it to have better accuracy for radiology, right? So if you, one minute, my slide is not moving. Okay, there. So you can see here that this is what we're going to do in our project. ImageNet is a huge repository of millions of images. So you use that, and then you do training, and you see in the middle, you see all these neural network layers. The input layer is shown in yellow, and the output layer is shown in red. And so in between, you have all these hidden layers. And the network, in this case, trained for 1,000 classes. And then now what you have is a model. And you take that model and you look at the bottom. You take a specific set of data that doesn't exist in a large format, and you fine-tune the model based on the new data. And that's kind of what we call as transfer learning. So now let's look at the proof of concept that we did. So we did this multi-cloud project. So we worked hand in hand with AWS team here. And then we did the following. So on premises, we did, see, in our case, we're assuming the customer has a lot of GPU resources on premises. And so in their on-premises data center, so the training is going to happen in the on-premises. Then once the training has happened, we then transfer the trained model to AWS. We extract the model into Sagemaker. Then we take take specific data associated with a particular class of objects, and we retrain the model. And then once we retrained and tested and found that model to be accurate for that domain, we then deploy the transferred model to what we call a SageMaker endpoints. So to do this training, first of all, we need GPU-based infrastructure. So we use the NVIDIA A100 GPU. This is the latest in a line of GPUs that NVIDIA has. GPUs are unique in the sense they can have thousands of cores, and they can do massively parallel computation. And the A100 has more than 20 times the throughput of its predecessors. And it also has 40 gig and 80 gig memory versions. And the 80 gig memory version is one of the fastest memory bandwidth in the world at 2 terabytes per second. So that we leverage that in our solution. So this shows you from a logical standpoint how it looks like. From we have a Linux node, which is a Ubuntu 20.04 node running on top of ESX, and we have A100 device in the server that we are passing through. We could leverage pass-through, or we could use vGPU. In this case, we use pass-through, but vGPU also would work very well here. And then what we did was we show you, we had 4 different VMs, each with one A100 GPU each attached, and 4 different ESX hosts. Each of these hosts also had Mellanox Connect X6 100 gigabits per network cards. These cards, we want to leverage something called RDMA over Converged Ethernet. That's what you see as RoCE. So RDMA provides you a lot of savings over the network, in the sense TCP/IP has a lot of overhead associated with it. RDMA eliminates a lot of that overhead and makes the product or the solution scale reliably. And then here you have the actual hardware we used. We used Dell R740XD hosts, which have GPUs cards in them. We use Infinidad-based petabyte class storage with the data, the large amount of data we had was stored in NFS. And then we had NVIDIA A100 per host, and we had ConnectX Rocky, right? So now let's look at the actual training components. So we used ImageNet, which is a very common class of data that's available. We got the entire data set for this project, and then we leveraged that for this project. And so some of the components, let's just whiz through this. It just shows you all the components that we use, the Python, the CUDA. CUDA is the framework that is needed for running GPU-based applications. Then you see the NVIDIA repository components needed for that version of Ubuntu. MPI is how you communicate via RDMA over the Rocky ecosystem. And then Horovod is the program that lets you distribute your training across multiple nodes. We have 4 nodes here, so we are distributing the training across those 4 nodes. So then here you see the classes. So this is the details of the classes. There are like 19,000 classes. There are literally 11 million images in this data set. We split that images into a validation data set. A portion of it has been apportioned to a validation data set, and another portion to the training data set. And then we ran the training across 48 epochs. So we go through multiple cycles of training. And so the 48 epochs stand for 48 cycles of training before we got the best model. And once we got this model, we passed it on to the AWS team, who then took it and then built their transfer learning on top of it. So now I'm going to pass it on to Rakesh, who will continue on relating to the work he did on the AWS.
Thank you, Mohan. Let me share my screen. Hopefully you cannot see the screen.
Yeah.
Okay. So let me first, as Mohan spoke about, so the model is being trained on the VMware side, and we're going to be taking the trained model and doing a transfer learning on the AWS side. And we're going to do this transfer learning using Amazon SageMaker. So let me first take a moment to talk about the AWS ML stack, right? And see where Amazon SageMaker actually fits in. So this is a zoom out level, like 30,000 feet level of what the AWS ML stack is. And the way to think about the AWS ML stack is actually made up of 3 different layers. At the very top layer, we have something called AI services. Now, the use cases like where you want to not create your own model, right? Where you want to just want to use an API, invoke an API endpoint and get the data. Those are for the AI services. So case in point, for example, if I want to do a transcription or if I want to do a speech recognition, we already have a model which is inbuilt. You could just use an API, invoke that endpoint and get the result. So if you want to convert a speech to text, you can use that. Or if you want to convert a text to speech, we have those API level type of service. That's what we call as an AI service. In the middle layer is where we have Amazon SageMaker. The simplest way to think about Amazon SageMaker is like it's a web-based IDE for a machine learning, right? It's from end to end, like what Mohan spoke about, like from labeling data all the way to actually training data, hosting your data, also monitoring your data. So SageMaker studios an IDE for machine learning, right? Whether you're a data scientist, whether you're a machine learning scientist, Amazon SageMaker is going to fit your use case. At the very bottom layer, we have what we call as an ML. This is for the bottom layer is geared towards deep learning practitioners. So these are the folks who are machine learning scientists who are going to be using a framework like PyTorch, TensorFlow, or creating a deep learning AMI, working with the infrastructure side. So the bottom layer is actually geared towards that, right? So when you think about AWS ML stack, these are the 3 different layers. And today we're going to focus on the Amazon SageMaker. We are going to be using Amazon SageMaker along with some deep learning containers. So this is a slide which we talked about, the whole machine development, right? When you think about machine learning, it's like labeling, collection. When you collect the data, then you spend a lot amount of cycles actually preparing your data, and you convert them into called features. And then you store these features in some feature store. And before you store the features in the feature store, you also want to check for bias in your data, because typically data is inherently biased from wherever the data is being collected. So you also want to remove the bias in your data. Then typically what we do is we take those data, we visualize them in the notebooks. Then based on your use case, you're going to select an algorithm. Either you're going to select an algorithm which already exists, or in some cases, you might actually build your own algorithm. Then you're going to use this algorithm, take the data, convert it into a model. And to get your final model, you're going to go through a very iterative process of tuning it. And that's what in the machine learning world we call hyperparameter tuning, where we tune it, we run through multiple iterations, we find out the best hyperparameters which will help your model, and then you create the model out of it. And once you have the model, you deploy them in the production. And once it's in production, we have to continuously monitor it, because your data can differ, right? Over a period of time, your data can change, and your response, your inference could change in relation to that. So you'll have to monitor your model. And whenever you see a difference in the model, like the prediction seems to differ from your baseline, it's time to actually retrain your data, retrain your model based on the new data set, right? And this whole thing is basically orchestrated with some orchestration flow. There will be a whole CI/CD pipeline. So this is a very high level view of how machine learning happens. Now, where SageMaker fits in is SageMaker is going to do a checkbox on each one of them. So as I spoke about, SageMaker is a web-based ID. So from everything from labeling to monitoring, the whole cycle the SageMaker will fit in, right? And we built the SageMaker from the Amazon SageMaker from the ground up to provide every developer and data scientist the ability to build, train, and deploy ML models quickly and at a lower cost by providing the tools required for every step of the machine learning development lifecycle in one integrated, fully managed service. Amazon SageMaker is the most complete end-to-end service for machine learning. It's a managed service for data scientists and machine learning operational teams that helps remove the undifferentiated heavy lifting associated with the machine learning, so that you in turn can have more time and resources and energy to focus on your business problem. So this is the overview of the SageMaker. So here we're going to actually break down into this 4 different boxes, right? One is preparation, what we spoke about, where significant percentage of the time is spent. So we have different, just like in IDE, you have different tools. Think of the Amazon SageMaker web-based IDE, you have different services. Like if you want to label, you have ground truth. You want to prepare your data, you have data wrangler. If you want to check for bias, you have something called SageMaker Clarify. And once the whole data preparation is done and you want to actually build, you want to author this, and you have Jupyter notebooks. So SageMaker has those notebooks. In these notebooks, either you can actually, in order to bring your algorithm, you can actually either use a SageMaker inbuilt algorithm, or you can build your own algorithm. You can bring your own containers. You can start from there. Then you're going to train the data, train your model using this algorithm and data. And we give you a managed training experience. You can, again, it's a very iterative process. So you are going to create a lot of experiments. And SageMaker can keep a track of each of these experiments, right? What was the outcome? What was the input? Like what were those hyperparameters? You can keep a track of each of those experiments. It also supports actually distributed training. It also has, just like any ID, whenever you're authoring code, you need a debugger support. For example, if you're actually doing a deep learning, you want to see whether your model is going to converge, or if the model is if it's going to diverge, or if there are some other issues with your model, right? So SageMaker also has debugger support for those deep learning models like PyTorch and TensorFlow. And when you think about training, the training happens on either on GPUs or CPUs, and these are very iterative in nature. on SageMaker in the cloud, right, we also support something called spot training. By that, what it means is that the excess capacity which AWS has, you can borrow those capacity using Spot at a very lower cost. Like, for example, up to 90%, you can actually get your training done cheaper out there. Once the training is done, then you actually deploy it. We give a again, managed deployment experience for fully managed, for ultra low latency and very high throughput. You can also use SageMaker through Kubernetes or Kubeflow. We also have an integration with that. We also support multi-model endpoints, and we also have the capability to monitor the model endpoints. So as we spoke about, like, as the monitor, as your model actually diverges from the base case, we can actually detect it, and we can actually then take action on it. And the whole thing can be orchestrated then using something called SageMaker pipeline, right, end to end. So Amazon SageMaker key benefits, again, it's like web-based ID is a boost of productivity at a reduced cost. Looking at the other angles of the SageMaker, for example, from a security point, it actually meets the strict security requirements for most of the ML workloads. From a compliance checkboxes on, for example, HIPAA, SOC, it can scale. It can scale with smaller data set to a very large data set, and it supports orchestration. So as we spoke about, like, SageMaker can actually train using either the inbuilt algorithm, which SageMaker inherently supports, or you can also bring your own algorithm. For today's POC, what we're going to show is we're going to use the SageMaker inbuilt framework, and we're going to customize it for our use case, and we're going to train using that. Right? And we're going to use a single instance for training. So let me switch at this point to the demo. And we're going to go through the SageMaker console. Okay. So what I'm showing right now on my screen, hope you can see my screen. So what you see on my screen, on the screen right now is Jupyter Lab, the notebook. Let me show you first where the data is actually stored. So the training which was done on the VMware side, it created a model. And that model is actually stored on an S3 bucket. Now, S3 is an object storage. And the whole model, what you see out here, is stored in one of those S3 buckets. Right? Then what we did is we're going to use this model, and we're going to author a code, and we're going to do the transfer learning. Let me also show the data set which we are going to use for training. So what we did out here is we took a data set called CIFAR data set, and this particular is a modified one. It only has a very small amount of data. There are 10 different classes out here, and each of those classes has 50 images. So instead of having thousands of images, this whole data set has only around 500 images. Right? So that's what Mohan talked about, like 500 images. If you want to do a full training, it's not sufficient enough to actually create a model with high accuracy. But what we're going to see is, because we are using transfer learning, even with 500 images, you can get a better accuracy with lesser training time. So this is the Jupyter notebook, and this is the authoring tool where you're going to go and write the code to do the transfer learning. We are using PyTorch. So let me first show the PyTorch code. And this is a very standard PyTorch code, basically, in terms of training, how the different loops work, how all the parameters are very standard PyTorch. There's nothing which is AWS specific out here. This is very standard PyTorch code saying, okay, read the data, do the learning. In the second notebook, what we have here is where we created our own Docker image. Now, this Docker image, what we did is we took the base SageMaker Docker image for PyTorch. We modified it, we enhanced it, and then based on the framework, what we needed. And what we did is what we're going to do is we're going to execute this code, this script within the Docker image. Right? And when you think about the cloud, the all these capabilities are actually provided on an endpoint, right? A public or a private endpoint. And these are all API driven. So what it means is, in order to invoke any of these, you just need to invoke those APIs. And these are available as part of your SDKs. In this example out here, we're going to use a Python SDK called a Boto3, right? In this Boto3, you can interact with the AWS endpoints. And in this case, we're going to interact with the Sagemaker endpoint. Say, Sagemaker, we want to do, what we're going to do is, we're going to tell the Sagemaker at a particular endpoint saying, take this particular Docker image and do the training for us. And all the necessary inputs, like where the image is, where your data is, and where the output is going to be specified. So this piece of the code, what we're showing out here is just trying to actually get a handle to the SageMaker session. In this case, we're getting a handle to the Docker image, which has been uploaded to the AWS registry. And to do the training, the only thing what you need to do is this piece of code. So here what we're saying is we imported some of the SageMaker libraries using the SDK. And what we are saying here is SageMaker, go and execute this particular Docker image. You can specify the number of instances you want to use for your training. Again, SageMaker supports training on a single instance. It also supports training using multiple instances. It can also support distributed training. So in this case, we're saying use instance 1, and we also specify where the created model needs to go to, right? You specify the output path, and you can specify the instance type. Now, in the previous training, what Mohan talked about, right? We trained on a very large amount of data set, and we had used GPUs out there. In case of transfer learning, the advantage what we're going to do is we're going to be using CPUs. The benefit what we're getting is, although we have less amount of data in terms of what to train, we can still use CPU to train that to get a bit and create a model with a better accuracy. Okay. So we are specifying an instance type out here, which is an AWS AWS instance type for machine learning. It's CPU based, and you can then specify the rest of the parameters like how much amount of disk space does the particular instance type require. So you can specify all those parameters out here. You can also specify the hyperparameters. Now, hyperparameters are the parameters which help the model, right? They are not the learned aspect of the model, but they are going to influence in terms some of those parameters like the epochs, like the number of times you want to run the training, the batch size, you can specify that. You see, one extra argument which we have specified out here is what was the original transfer model? Where is the original transfer, the model which was created? As we saw before, this particular model was actually created and put in an S3 bucket. So we are specifying where that S3 bucket is, so that when the training starts, what the code is going to do is it's going to take that model from that S3 bucket, download it to the instance, and then it's going to actually do the fine-tuning aspect. In the fine-tuning, what we're going to do is we're going to carry the weight as it is what was initially in the model. We're going to change the last layer. The original model was created for classification of multiple images, like more than 10. In this case, we only have 10 different classes. So we're going to change the last layer. We are going to just say we only want to do a classification for 10 different classes. And we're going to start from there. So instead of actually having the weights which are randomly initialized, in this case, we are carrying the weights or the information from the prior train model, and we're going to start from there. So we're going to fine tune this. And then the rest of the parameters, what we're specifying is where is my training data? So in this case, as we saw, the training data is also in an S3 bucket. So we specify where the training data is and where the validation data is. So we specify this, and in order to start the training, you just call this one single command. Let me actually start out here as we speak. So here we have the Docker image, and I'm just going to call this fit, and this will start the training. And this is going to kickstart the training. Now, as with cloud, right? You don't have to actually have your resources running 24/7. You only pay from a cost point of view, you only pay for the amount of time which you're using for training. So at this point, what is happening when we call the fit? from the SageMaker. SageMaker is in this infrastructure is going to spin up this instance dynamically. It's going to actually download those Docker image. It's then going to start your training. And once the training is done, the whole infrastructure is toned down, right? And from a cost aspect, you're only paying for the amount of time the training was run. So here the training started, and we'll keep this running in the background. We'll see the previous run results, which I have run previously, and we'll see how it looks like. So here I go to the training, and I can get a list of all my previous running training jobs out here. So these are the list of all my previous training jobs, and you might see here there's one more new entry. This is the training job we just started. Okay. And as this is working, let's see the previous run, how it looks like. So it's the same code which ran previously for transfer learning. And as you see, it actually gives you a list of all the inputs, whatever was specified. You can see the details out here. You can see the metrics like CPU, memory usage, disk utilization, everything out here for that instance which was dynamically spun. And if I want to see the details, I can go to the click logs, and the output of that run, like the output of the code, you'll be able to see in this CloudWatch log. So here I go, and I'm going to click out here. So here, all the output from that log is actually, you can see it out here. So it shows you in the code we are emitting out the accuracy of the training and the validation. So you see it shows you the training accuracy, training loss, and validation accuracy. Okay. So that's the SageMaker training experience. So to summarize, right, in order to just do the training, it's basically just invoking a Boto3 library and just specifying your input parameters, specifying which container you want to use, specify where your data sources, and just call the fit, and you can do the training. You can select the instance type based upon your use case. In this case, we are using transfer learning, so we're using CPU. If you want to use GPU, there are also GPU type of instances available. Now let's look at the output of what was the what was the result. So this is a code, what we just showed on the notebook. Now here, in order to compare anything, we need to first create a baseline, right? So what we did is we did a training for 20 epochs, but we did not use transfer learning. We used the same network, but we did not use the transfer learning model, right? So this would be as if something is starting from scratch, right? And you would see that because we only have less amount of data, we only had 500 images, 10 different classes, and running for even for 20 epochs, you would see that accuracy is not that great. Again, you could actually do more tuning to this. We did not run hyperparameter tuning or any other tuning, but even with tuning, because of the less amount of data, you would have to create more synthetic data by doing a lot of image transformation to increase the accuracy. So there will be more iterative work which needs to be done out here, right? In order to get this accuracy anywhere to your reasonable expectations. So let's compare this, the full training, with the transfer learning. So it's the same network. The only difference between this one is the same network, but we took the weights, we took the pre-trained model and trained that, and using that pre-trained model, we did this training. In this case, you would see that within 20 epochs, the accuracy for both the training and validation goes past beyond 90%, right? So this is the benefit of using a transfer learning. So to summarize, the advantage what we see is you could do the training in less amount of time, right? To get a higher accuracy. You could get it done cheaper because you can use something like a CPU out here. And using Amazon SageMaker, you only pay for the time the job is run. So from a cost perspective, it becomes very efficient. Moreover, you can add spot instances, and this could actually make it 90% cheaper than traditional training. Now, once the training is done, the next step comes in the inference. So let me show you how it, from a demo perspective, how it looks like. I have taken a different model and hosted it on the SageMaker endpoint. In order to actually host a model, now there are two ways to do this. Either you can do a batch inference, or you can actually do a real-time inference. Now, batch is where you're not actually getting where you have bulk of data. You want to get a batch prediction. Or real-time inference is when you're actually sending a real-time request and you're expecting the very low latency response back. Right? SageMaker supports both. So in SageMaker, you can create an endpoint configuration, and in endpoint configuration, you can specify, okay, what your model is, and what type of instance you want to use, and how many of these instances you want to use. Just like anything with the cloud, right? The system has a capability to scale out and scale in based upon a particular metric. You can also support different variation on a particular endpoint. For example, when you are especially doing the experimentation, you have, say, model A, and you have other variant of model B, and you want to actually put both model A, variant A and B on the same endpoint, and put some amount of traffic in A and some amount of traffic in B, SageMaker endpoint configuration will allow you to do that. Right? So using endpoint configuration, you can select those different variants, you can select the different types of instance, you can define how you want to scale out and how you can scale in. So once you define the endpoint configuration, then you can just create an endpoint, and it will give you an endpoint which you can invoke through an API to get your response back. Let me go back to the slide out here. Okay. Let's see how that actually looks in terms of how does it really work, right? So before we go there, one thing too we want to actually also come back is, like, from a machine learning perspective, most of the cost is driven by inference, not training, because when you think of training, this is an industry type of benchmark, like 10% training and 90% inference, because especially for real-time inference, the endpoint is continuously up and running. And from a model hosting point of view, as we already spoke about, SageMaker endpoint actually gives you a very low latency, high throughput, and it gives you 99.99% availability. So this is what we did for this particular POC. So we did the training. In this case, we did the training on-prem, like on the VMware side. We took the train model, right? And we put the inference code, and then we can use it either for real-time inference or for the batch, and then you can get the prediction. If I peel the layer, like what the endpoint hosting looks like, what internally happens is when you actually invoke the endpoint to actually do the hosting for you, SageMaker will spin up those instances in different AZs based upon your configuration, will download those images, put behind a load balancer, and give you an endpoint. And this endpoint, then you can hit either via Lambda, which can be faced by API gateway from some client application. This is a typical flow, right? How a customer use it. So you have an API gateway, you have a Lambda, which will invoke this endpoint. And this whole thing is provided with this whole AZs and this whole instances which are spun up, which behind the load balancer, everything is set up by the SageMaker. Now, what are the different options for actually basically hosting it, right? Now, depending upon what your model is and what throughput you're looking for, we have four different options out here. So if your model is very small and the throughput expectation is very low, you can host this model on a CPU. On the other hand, if you have a very large model and you require a very low latency access to CUDA, you can host this endpoint on GPU. We also have an option where you have a mid-sized model and you have a low latency budget within a tolerance limit. You can get partial GPU. You don't have to have an entire GPU. You can have partial GPU attached to your CPU, what we call as an elastic inference. Right? So you could even, when you host it, you can say, I want to use elastic inference. Now, AWS also has released its own custom chip called Inferentia. Now, Inferentia is for very high throughput, high performance for basically deep neural networks. It is around 45 is approximately 45% cheaper than basically GPU type instance, especially when you're using PyTorch, and it's very good for pre-trained models. So using these different combinations, you can figure out, okay, based upon your requirement, how do you want to host it? And as we connect back, right, most of the cost in the machine learning world is when you're actually doing the hosting, when you're doing the inference. And how do I actually invoke an endpoint? This is again a code. If you look out here to invoke this particular endpoint, it's again an SDK. It's just an API. You just say, hey, runtime, just invoke an endpoint, specify where the endpoint is, and it will get you a response back. Hopefully, this gives you a good overview of what the SageMaker is and how we use SageMaker for doing the transfer learning. And you might also see the advantage of doing a transfer learning out here, that the overall training time in this case did not take more than an hour, right? So it took only under an hour, and we ran for 20 POCs, and we used a CPU. So these are the benefits of using a transfer learning over doing a complete full training. That's it from me. Handing over to Mohan. Mohan?
Stop sharing.
Yeah.
Okay. So we're almost at the end of the hour. So let's wrap up here. So and here, what we see is the future of AI/ML in multi-cloud is that enterprises are rapidly adopting multi-cloud frameworks. There are cloud providers that provide specialized functions and capabilities, like you saw in AWS Sagemaker, that enterprises want to leverage. Maybe they want to deploy in the edge. So there are all these providers out there, and so we want to, looking at from a customer standpoint, customers want to potentially use the best of both worlds, the on-prem world and the cloud world. So this project that we showed you demoed that we can have AI/ML training on-prem and processing and transfer learning in the cloud. So and also we can take those AWS endpoints and have inference happen in edge locations, different time zones and different locations that AWS supports. So that's kind of what this POC hopefully showed you. And the key takeaways from this is the VMware platform, it supports a lot of capabilities for machine learning. We use that to take a large model and train with that millions of images, and we trained over a short time, and then we're able to use that model in AWS SageMaker using transfer learning, and then deploy to endpoints as well. So through this, we basically have shown that multi-cloud is a reality. In AI/ML, you can have different parts of your infrastructure in on-prem and on the cloud. So, and then last but not the least, here are some resources that you can look at. We will blog this solution in the next few weeks, so you would see that solution in the machine learning blogs, and there's a reference to SageMaker as well. With this, I'm done. So passing it on to Teresa.